Hi folks! In this video, we will deal with multiple linear regression. We'll try to understand the concept of it, how to compute the parameters vector. Take a look at the following expression. Y sub I equals to b naught plus b1 x sub I1 plus b2 x sub I2 plus b3 x sub I3 plus and so on plus bm x sub im plus the residual term e sub I. In the previous video devoted to bivariate linear regression, we had the case when y was only dependent on x. And in this video, we extend this method onto multivariate case where we have more than one factor with which we model the behavior of y variable. We presuppose that dependence is linear. And in this case, the coefficient which is associated with the corresponding factor shows the influence of this factor onto the target variable. For example, if this coefficient is positive, that means with the increase of x1, given all other factors staying the same, we can expect the increase of y by this value, by the value of this coefficient. If we increase x2 by 1, for example, we can expect on average y increase by this value or decrease if the coefficient is negative. The only question is how to compute the parameters given the statistics that we have. For the sake of simplicity, let's introduce the following matrix notation. If we put all the observations of the target variable into the column vector, we will denote it as y, the vector of the target variable. Matrix X will look like this. The first column will contain just ones, and all the others will be devoted to the corresponding factor. For example, the column number 2 will reflect the statistics on factor 1. The column number 3 will reflect the statistics on x2, and so on till the factor number m. We denote the parameters vector as capital B and the vector of the residuals as E. Then if we use this notation, this model can be written in a concise form like this: y equals to xb plus E. Indeed, take a look at this. If we model y sub 1, you see y sub 1 is the first element of this column, and it will be equal to this row multiplied by this column, the scalar product. What would imply y times b naught plus x11 times b1 plus x12 times b2 and so on till x1m times bm. What is exactly this form, and plus e sub 1. So that is how y sub 1 would be modeled in this case. And then it goes on the same for y sub 2 and so on till y sub n. In order to compute the parameters, we resort to the same ordinary least squares method, just like in the video devoted to bivariate linear regression. And there we minimize the sum of squared residuals. In this case, we will do exactly the same. Our target function will look like this. You see q of b equals to E transpose E, which is just another way of writing sum of E sub I squared. If we express E from this formula, we will have E equals y minus xb, and if we replace E with this expression here, we will get this. And if we remove the parenthesis, we will end up with y transposed y minus, you see, if we transpose xb, according to the rules of linear algebra, we will have b transposed x transposed times y minus y transpose times xb plus b transposed x transpose times xb. And by minimizing this target function, we will find the vector of the parameters giving us the least squared error possible. Now take a look at these two terms, this one and this one. What can we say about them? They look pretty the same. You see, here we have B transpose, here we have B, X transpose and X, Y and Y transpose. Let's take a look at the size of these matrices. Look, B transpose will be of size 1 by m plus 1. Why? Because we also account for B naught. X transposed will be of size m plus 1 by n. You can clearly see that by analyzing this matrix. And finally, Y will be of size n by 1. Now it can be seen that the output matrix, if we multiply these three, will be of size 1 by 1, since the size of the product is defined by the outer dimensions of the matrices being multiplied. So we came to the conclusion that this would be just one number. The same goes for this term. You see, Y transpose will be of size 1 by n, X will be of size n by m plus 1, and finally B will be of size m plus 1 by 1. And here we will also end up with just a scalar one number. If we transpose a matrix containing only one number, it will be the same number. So try to transpose this term. What will it look like? It will look like this. You see? That would be B transpose X transpose times Y. So that's how we show that these terms are identical. And we can just put them together and can simplify the target function. It will look like this. You see, we write here 2B transposed X transposed Y. And then we compute the gradient, which is the vector of partial derivatives of our target function, and will look like this. You see, if we consider this term, if we take the derivatives on B, it will be equal to 0 for all B's. Then this one will be equal to minus 2x transposed Y, as if B was just one number and not a matrix. And this one will be 2x transposed xB, as if B was just a number and not a matrix, since B transpose B can be perceived as if it is B squared. And then the derivative of B squared is just 2B, what explains this outcome. And from this expression we get X transposed XB equals to X transposed Y. And from this expression we get the ultimate analytical form for parameters vector B that looks like this: X transposed X inverted times X transposed Y. This is how we derive this formula from scratch and use it to compute the vector of parameters V for multiple linear regression. Please refer to the next videos. Goodbye.